we are going to learn the Dirac formalism in quantum mechanics, and in doing so let us start from the idea of n-dimensional vector space. Okay, just a sec. Yes, I'm done. Now let us start from the very beginning. What we do know about the three-dimensional vector space. Let us consider this vector, a vector, in three-dimensional space where e1, e2, e3 are the unit vectors along three axes in the orthogonal representation of 3D space. That means e1 dot e2 is 0 and e1 dot e1 is 1. So if one want to write the vector a vector, it is any vector where a1, a2, a3 are the three components of the vector along three axes. If you want to write this in matrix form, that is equation 1 in matrix form, you can write if A is represented by a column matrix with its three components along a single column, that is like this a1, a2, a3 in a single column, that is this matrix is 3 cross 1 matrix. Okay, then you should choose e1, e2 and e3 like this 1 0 0, 0 1 0 and 0 0 1. Then satisfy this equation. You see this equation is satisfied by this assumption, that is a1, a2, a3 is in the left hand side, and if you multiply e1 matrix by a1, that is e1 is what 1 0 0. If you multiply by a1, then a1 element will come at the first place, that is this matrix a1 into e1 is also a column matrix which is equal to a1 0 0, and the second term will be 0 a2 0, third term will be 0 0 a3. So if you add three column matrices, then it will give you a1, a2, a3, this one. So it is satisfied. So this is the matrix representation of a 3D vector space. Okay, now this one is written here. Now if you have two vectors, now if I talk about the vectors, you should assume that I am talking about the column matrix. So A and B are two different vectors in a vector three-dimensional vector space with components a1, a2, a3 and b1, b2, b3. So if the inner product you want, inner product means you are familiar with dot product or the scalar product name, but inner product is also a similar name of scalar product. So a dot b, but it is written over here, you can see a comma b, because we are multiplying two matrices, so different symbol is used, but the meaning is same, that is the component of a along b. Component of a along b is a dot b, which is ab cos theta, you know, where theta is the angle between a vector and b vector. It is a scalar representation, but if you want the matrix representation, then a dot b will be written like this, which is the same meaning, that is a dot b you can write in another way, that is a1 b1 plus a2 b2 plus a3 b3 in your familiar vector notation, but in which is written here, you can see a1 b1. It is also coming from the fact that the matrix representation you will also get these terms, because how you will get this from matrix? A dot b means you should multiply A transpose to B or B transpose or B transpose to A. That means this column will be represented by a row matrix. Okay, so if you transform this like A transpose matrix, that means a1, a2, a3 will be in a row, that is it will be 1 cross 3 matrix, and this is 3 cross 1 matrix. So if you multiply both of them, the result will be 1 cross 1 matrix. That is nothing but a scalar, which is written over here, a1 b1 plus a2 b2 plus a3 b3. Now if we make our life more complicated in thinking that n dimensional vector space is there, so n number of unit vectors are there which are mutually orthogonal, e1 e2 dot 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 en, and you can represent the vector as a1 e1. A1 is ai's are scalar, so a1 e1 vector plus a2 e2 vector plus dot 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 an en vector. You can represent this in your vector formula. And now another vector b vector in that n dimensional vector space, then a comma b, that is the inner product, that is scalar product between a and b, will be the sum over ai bi. It is written by comparison to the 3-dimensional vector space. That means we are using the 3-dimensional result into the n-dimensional vector space. So if now the components of vectors are if now you assume that the components of vectors are not necessarily real one, then the result should be written like this. Here it is written, that is sum over ai star bi. Ai star is the complex conjugate of the component ai. Okay, so this is your complex, this is your n-dimensional vector space in complex plane. Okay, and the inner product is defined like this, and the norm of a vector, that means length of the vector, that is the magnitude of the vector, is nothing but a1 dot a1 is equal to a square, a dot a is equal to a square. That means a is equal to what? Root under of a dot a. You can write this, and this is called norm in n-dimensional vector space. Generally it is called norm. Norm basically the magnitude of the n-dimensional vector. So this is also written by comparing with the 3-dimensional result, and this is shown here. If the vector is normalized, that is it may so happen that in n-dimensional vector space a vector is a unit vector, so its magnitude should come 1, so n should be 1. How n should be 1? So perform a comma a, that is a comma a means sum over ai star into ai, okay, using the inner product formula. So a1's ai star ai is your mod ai square, so sum over mod ai square should be 1 in case of a is a normalized vector. Okay, if it is not normalized, then it is not equal to 1, but it is something, some value, some positive value is there. If two vectors a and b are said to be orthogonal, that is a comma b should be 0. Okay, and in n-dimensional vector space, a set of n vectors, that is a1 to an vector, are said to be linearly dependent if there exist scalars, some scalar, not all 0. That means if you can write this equation, that is the superposition of n vectors with different coefficients, that is c1 a1 plus c2 a2 vector plus c3 a3 vectors dot 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 is equal to 0. Such equation, if such equation exists, then you should call that a1 to an vectors are linearly dependent. That is, there is a relationship between the vectors a1 to an. If that would happen if if the coefficients c1 to cn, some of them or all of them exist, that is not equal to 0. Okay, if all of them are independently 0, then a1 to an vectors will be called as linearly independent vectors. You know this from the discussion of vector analysis. This is well known facts, you also know. Now if you have a set of n linearly independent vectors, okay, we are considering n linearly independent vectors a1 to an, then there may exist any vector phi which can be expanded into a basis set of the a1 to an vectors. That is, any vector can be constructed using these vectors. What is the example of that? The example is e1, e2, e3 are the unit vectors. See, it is written over here. Yes, number 1 equation. Here you can see any vector, a vector can be written as a superposition of 3 unit vectors with different coefficients a1, a2, a3. How we are able to write this? Because e1 vector, e2 vector and e3 vector are linearly independent. Because e1 vector dot e2 vector is 0, there is no relationship between e1, e2 and e3. They are 3 mutually perpendicular and also independent vectors. So we were able to write any vector in terms of the basis set expansion of ei vectors, that is e1, e2 and e3 vectors. So we have written also in another vector, b vector is written in terms of e1, e2, e3 also. So in n-dimensional vector space the theory is same. It is not written by e1, e2 dot 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 en, but it is defined by a1, a2, a3 dot 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 an. Not necessarily they are unit vectors. Okay, any independent vectors are can be used to form a basis set, and in terms of those n independent vectors you can write any other vector, like phi is written here. Phi is a vector which is written as ci ai vector, and sum is there i1 to n. So this is the generalized form of n-dimensional vector space, and how any vector can be written as n-dimension as a basis set expansion of n number of linearly independent vectors. This is the knowledge you can get from here. Now let us move on, because we are not talking about the vector in quantum mechanics. Yes, we are talking about vector, but in different form. In different form means in wave functional form. Here the vectors are the wave functions. So to take an inference from the n-dimensional vector space and form the new methodology to study the quantum mechanics, Hilbert space is defined. How Hilbert space is defined? See, it is written as, in the vector space we considered the unit vector c1, e2 dot 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 en form the orthonormal basis set, that is linearly independent and mutually orthogonal to each other, and e1 dot e1 is 1. So here these are unit vectors. Alternately, a space can be defined in which a set of functions phi 1, phi 2, phi 3 dot 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 form the orthonormal unit vectors of the coordinate system. Okay, so we can think about a space which is defined by a set of functions phi 1, phi 2, phi 3. It for the sake of simplicity it is written as that those functions are only dependent on x, single variable functions. So there can be found some functions, n number of functions which are orthonormal, just analogous to the orthonormal vectors in n-dimensional vector space. such that any other functions can be written as the basis set expansion of those phi 1, phi 2, phi 3, just like this formula. Replace a1 by phi 1 and any function f can be written as the basis set expansion over phi's. So this is the idea of Hilbert space, and in Hilbert space it is to be mentioned that the number n should be infinity, that is infinite dimensional linear space is called a function space, that is Hilbert space. Okay, so n number of orthonormal sets are there, infinite number of orthonormal sets of functions are there which can be used to form a basis, and from there you can form any other functions in terms of those functions. Okay, there are some examples of that. You can take an example of Legendre polynomials. So Legendre polynomials are those linearly independent functions which can be used to expand any other functions into the basis set of Legendre polynomial. In your mathematical physics you can check this fact, and this will consolidate your idea about the function space. Okay, so we are talking now, we are going to talk now on the theory of quantum mechanics, on the methodology of quantum mechanics, and in the Hilbert space. Okay, so in the Hilbert space there are some other properties also. So any two vectors of the space are phi and psi. Psi and phi are two vectors. Here you should be aware of the fact that the vector means the function. Okay, here the term vector come from the n-dimensional vector space. As the Hilbert space is analogous to n-dimensional vector space, the properties of n-dimensional vector space are there in the Hilbert space also, but it should be mentioned that in Hilbert space you are not going to write any vector sign. The functional form, the function space is meant here by the Hilbert space. So two vectors mean two functions, phi, psi and phi in a Hilbert space. Then a multiplied by psi plus b multiplied by phi is also another vector in that space, where a and b are the scalars. So distributive laws will follow, and associative laws are followed, that is a into b psi is equal to ab into psi. There is no harm in writing. So commutativity, associativity are the properties of the Hilbert space. Second property is the inner product. Inner product of two vectors, that is two functions psi and phi, is defined as the integral of phi star psi dx, which is in the interval a to b, because your dx x is the lower limit of x is a and the upper limit of x is b in one dimensional calculation. This product is called inner product, and this product is something like that, the expectation value we may call, but this is something like I will tell it later. The property of the Hilbert space is that this integral is finite. Forget about this symbol in the left hand side, just focus on this integral. You have two functions psi and phi, and x is the variable on which the functions are dependent on, and you are going to perform an integral from a to b, where the a and b are the limits of the region on x. So this integral, just consider this integral, forget about this sign, phi star psi dx. This integral is finite, should be finite if phi and psi are in Hilbert space. Okay, so this integral is named as inner product, and its symbol is psi comma phi. If psi comma phi is there, there it is written psi comma phi, but here it is meant actually phi comma psi. It is correct. What is it is written is correct. Phi comma psi. It is the symbol of the inner product, just like the n-dimensional vector space where a comma b was there. A is a vector, b was a vector, but here psi, here phi is a function, and psi is another function in Hilbert space. So phi comma psi is the inner product between phi and psi, is defined by this integral, which is finite. Okay, and what is it? What does it mean? It actually means the component of phi on psi. That is, it is abstract. This thinking is abstract. It is not your bread and butter type thinking, but you can understand very easily if you keep in your mind that the idea of n-dimensional vector space. In n-dimensional vector space, a vector and b vector, in place of a vector and b vector, phi and psi functions are used, and they show this property, which is finite, that it may be negative, it may be positive, but it is finite, not infinite, not divergent result you will get from this integral. Okay, so this is actually physically this integration actually physically means that this is the projection of the function phi on the psi. Okay, we are not able to draw this because this, first of all, this n-dimensional space and the function is there, not vector. It is following all the properties of vector, but you cannot draw a geometrical diagram on this. Yes, you can try some books. There are some pictures how this integral is projection of one function on the another. You can find it some standard quantum mechanical books. You can follow them, but I am not going into this. Now the norm of the function, where in the n-dimensional vector space you saw that the norm of there is the norm of any vector, a vector. If it is normalized to unity, then the norm is 1. If it is not, it is not 1, it is some positive scalar function. Here the norm a comma a, that is sum over ai star into ai, is there 1 to n, and in Hilbert space the norm of a function is defined as similarly phi star phi, that is mod phi square you can write, and in another notation phi comma phi can be written, or this notation I will come into that. What is this left hand bracket and right hand bracket notation? This is the bracket notation. I will come into that. And if you replace, see this equation, the projection equation, if you replace phi by psi, that means or psi by phi, then phi comma phi will be there, so integral will be phi star phi dx. So phi star phi dx, and you know phi star phi, if that phi is a wave function, then phi star phi is the probability density, so it should be greater than 0, and the total result will be another probability of finding the particle between minus infinity to plus infinity should be greater than equal to 0 and finite. Why greater than equal to 0? It should be you are thinking that it should be 1, as it is probability. If phi is a wave function, no, not necessarily phi is always the wave function, so it is greater than equal to 0 and finite. Okay, it may be 1, it may not be 1. If it is not normalized, then it should not be 1. If it is normalized phi, then should be 1, but the rule is greater than equal to 0. It will be kept in your mind. See what a beautiful thing you can compare it with the vector idea. Say two vectors, you are taking the inner products, that is the scalar product, a vector dot b vector. It may be negative, it may be positive, or it may be 0 if they are orthogonal to each other. Okay, so finite is there. So it is resembling the idea of vector dot product, that it is finite. It is here, it is not written that it is positive, it may be negative. But if you take the inner product of two same vectors, that is a vector dot a vector, it cannot be negative because it is a square, so it is always positive. So here you can see the norm of the function phi is just the phi star phi dx a to b is greater than equal to 0, that means positive. So the examples are there to remember the Hilbert space formulas. Now let us take a look on the orthogonal functions. Here the similar thoughts are there. F comma g, f and g are two orthogonal function. If they are orthogonal, then the inner product should be 0. If they are normalized, that is f comma f should be 1. Okay, just like the vector formula. And in a smaller form, this is written like this. So the advantage of writing this this symbol, that is f comma g in first bracket, it will make very easier to write these integrals, because all times you will get tired of writing such integrals. So one can understand f comma g, what does it mean. So this symbol is very much useful in writing. So fi comma fj will be delta ij. It is the general of 2, 3a and 3b equation results. How? Kronecker delta ij, you all know that ij, if they are equal, then it is 1, and if they are not equal, then it is 0. So two functions inner product will be 0 if they are not equal and they are orthogonal, and if they are equal, that is fi comma fi will be 1. So this is a very smaller form which can be remembered in short. In place of 3 and 3b, you can remember this. It will help you to write those equations in very shorter way. And now it is very basis set expansion. If you have n number of or infinite number of linearly independent equations, functions, so these are called here the definition of linear dependency is there. I am not going into this. Now if you have a set of linearly independent functions f1, f2 dot 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 f infinity maybe, so you can write any other function. See what I am talking from the beginning of my class. Any other function can be written as a superposition of such functions which are orthogonal to each other and form a complete basis set. That is, no other functions are required to put into the sum. These functions f1, f2, f3 dot 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 f infinity, as you were talking about the Hilbert space, so it is infinite dimensional space. So infinite number of such orthonormal functions are there, and it is sufficient to represent any other function, any arbitrary function phi, in terms of the superposition of such functions with some constant coefficient ci. So this is called basis set expansion of any function in terms of orthonormal linearly independent functions fi. Okay, and now ci can be found out from the equation number 4. How? Multiply or take the inner product, the both sides, take the inner product of phi to a phi. So phi comma a phi will be within the sum Ci fi comma phi fi. So fi comma fi is your delta ii, that means I is there, so sum will be vanished and Ci will be left in the right hand side. So Ci is equal to phi comma fi, or you can write in converse way fi comma phi. The meaning is same, it is commutative. So Ci can be found like this. I will come into this detailed calculation of Ci. It is simple, but I will show you in steps in the latter of the lecture, where I will talk about the expectation values. I will come into that point. Now let us take a look on the revolutionary notation method, I should say, in quantum mechanics. That is the Dirac notation, which is known as Bra-Ket notation. Here what we are writing the inner product in terms of a first bracket psi comma phi or phi comma psi, whatever. So here it is written as psi comma phi. Now Dirac replaced the sign as some meaningful using some meaningful symbol. Here you can see the left angle is there, left angle it is called. So left angle, then psi, then a vertical line, then phi, then right angle. This is the symbol, and which means nothing but what we know already, the inner product of the psi and phi, two functions in Hilbert space. So psi star phi dx minus infinity to plus infinity. So what is this and what is this? What is the meaning of left angle and what is the meaning of right angle? Why they are different to each other? What is the meaning of this symbol? It is written over here. I discussed already this thing. I am not going into this, and you can check some property. Before checking the property, let's take the what is called this left angle thing, that is a psi, left angle psi vertical line is called the Bra vector, and the right vertical sign and the right angle within which phi is there is called the Ket vector. Okay, Ket vector, and together they form the Bra-Ket. First there is a Bra and there is a Ket, and what is that? Ket means your Ket means a function which is obeying all the laws in the Hilbert space. Okay, and Hilbert space is infinite dimensional space and complex in nature also. So it has a dual character, that is the Ket psi. Psi is a function in the Hilbert space. It is written like this to signify something which I am going to tell you. That is this symbol psi. Forget about this symbol, that vertical line and the right angle. Just forget about that. Just concentrate on the psi. The psi is a function in the Hilbert space, and it has another, its dual representation, which is called the Bra, in that Hilbert space also, in that complex Hilbert space. Okay, just like your real number, and no, not the real number, is imaginary number which has I. Say I is the imaginary number, that is root under of -1. It has a dual character which is I star. I star means minus I. So just like mirror reflection. So in complex plane the imaginary numbers have dual, have their dual or their canonical form. The name canonical is not used, but I am excited, so I am using this. that I in the complex plane is an imaginary number which has a dual character, which is minus I in that complex plane. So in case of a function, not a number, it is a function psi, and the psi is called the ket, which has the same kind of representation, which is a dual representation of that function. So how you will represent those two, because they are different. See, they are I and minus I, they are different quantity. So the phi and that dual phi are different from each other. So one symbol is written like this, and another dual character is written like this. So their both ways symbol are used to signify this is the dual character. So if you want to go from Ket to Bra, the path will be like this, and if you want to Bra to Ket, the path will be reversed, just like an imaginary number. If I is you want to make the I as minus I, so you should reflect I into minus I, and if I minus I star you take, then the result will be again I. So similarly, the functions Ket and Bra are signifying the same thing, but in Hilbert space, in complex space, okay, in infinite dimensional space. That is different from a number, imaginary number, and the Ket function. So Bra-Ket algebra is there, and obeying this symbol, these symbols are given by Dirac, and you should follow this symbol. That is, in Bra, what is written in Bra should be reflected by star. What is written in Ket should not be reflected by any star. So Bra, psi, Ket, phi is actually which means actually an integration. It is nothing but an integration. It's nothing but an inner product, which is where psi star is there and phi is without star, and dx, and integration is minus infinity to plus infinity. Okay, so be careful about these symbols. And now let us take this property, and I will suggest that these properties should be proved by yourself, and in a simple manner you can prove this. If you understand this equation 5, then this will follow. These 4 relations will be very easily you can prove. The bracket, usefulness of bracket notation is that using this formula, the algebra, the difficulties with writing such integrals will be overcome by these simple algebraic relations. Okay, but keep in your head all the time that writing this type of bracket notations, you are actually doing some integrals. So the first property here, it is psi, and in Ket there is a phi is equal to a. That is, put a phi in place of phi in the above equation, and a will be there multiplied with phi, so a will be come out of the integral. So this, what is that? This is nothing but psi phi. So bracket psi phi. And if the scalar in the bra, then see from here a psi phi, what will be that? So multiply psi by a, which will reflected by a star psi star in the integration. So a star will be come out of the integration. So again the integration is psi phi, but the multiplication factor is not a, it is a star. So you will remember like this, if one scalar is multiplied in the bra, it will come out of the bra because it is nothing to do in the integration, but in complex form, that is A star, and this relation is very much important. Psi phi whole star is equal to phi psi, because the inner product you can prove this very easily. I will suggest prove those relations by your own. And this is a distributive law, it will follow. Okay, there, see, I am again coming to the fact that it is a dual representation, and Ket psi is represented by a bra phi in dual space, in Hilbert space, and one-to-one correspondence between there, that is unique bra is there. For a unique Ket there is an unique bra, and for unique bra there is a unique Ket. Okay, so A psi plus B phi, this is another Ket by superposition principle or by the distributive law, it is written here. Okay, this can be distributive law. So A psi is another Ket, B phi is another Ket. So by adding them it will form a different Ket, A psi plus B phi, which has another dual, an unique dual, which is A star psi plus B star phi, because in dual space you are taking the complex, as because this formula is here. It is checked by this integration, you can check this formula, all formula can be checked, what is written over here. Okay, so this is very interesting one, these two relations. A psi is equal to A out of psi, but in bra if A is there, then outside the bra it will come, but with a complex number. As I have told, it is written in this equation, you can understand by this relation also and using this integration formula. Properties of scalar product, yes, it is proved here, that is phi bra phi Ket psi whole star is equal to bra psi Ket phi. The inner product, if you take the complex conjugate, it will reverse its order. How? Let us consider phi psi whole star, then according to the formula phi psi, phi star psi integration. Oh, look here, the integration is written in the 3D, so dq bar vector is there, so don't bother about this. So phi star psi integration, within the integration it is there, and whole star is there. Whole star means this will be starless because this is a scalar, and phi this will be on star. So psi will be star now and phi will be without star, which means that it is actually bra psi Ket phi. So phi psi bracket within the bracket bra phi Ket psi whole star is equal to bra psi Ket phi without any star. It is proved. It was in the above relations, and similarly you can formulate this all the bracket relations using those above formula. Now I am coming to the Hermitian operator. What is meant by Hermitian operator? I have already discussed what is Hermitian operator, in which was in our quantum mechanical postulates, but there the bracket notation was not used. So now let us understand the Hermitian operator and the properties of Hermiticity under the light of the Dirac's bracket notation. Here you can see an operator A is there, and its Hermitian adjoint is defined, is symbolized like this, A dagger. Okay, A is an operator, quantum mechanical operator, and A dagger is the Hermitian adjoint of the operator. Why Hermitian operator? Hermitian adjoint is defined by this relation. that is within the bracket psi a dagger phi is equal to phi a psi whole star. If this relation holds, then a dagger should be called as the Hermitian conjugate of the operator A. Okay, not Hermitian, Hermitian conjugate. For the it is the definition of being an Hermitian conjugate or Hermitian adjoint of an operator A. This is the formula. This to be remembered. Okay, the properties of Hermitian conjugate rule. If a scalar, you take a scalar, its Hermitian conjugate is nothing but its star, that is its complex conjugate form. Okay, and if you take the Hermitian adjoint of Ket, it will give you the bra, that is Ket psi whole dagger, Ket psi dagger is equal to bra psi, and similarly bra psi dagger is equal to Ket psi. Okay, and there are some formula. This will be understand very easily. This formula can also be understand very easily, that is see, alpha is a scalar constant, alpha a psi within a Ket. See, let us understand the meaning of a psi. Psi is a function, a is an operator, so operator A operating on psi will give you another function. So an operator, say suppose d dx is an operator, it is operating on x square, what you will get? 2x is a function. So when operator operates on a function, it will form another function, not necessarily another, it will form similar function also. If e to the power x is there and d dx of e to the power x is again e to the power x, but function is there. Similar or different functions it may form, but function will be formed. So a psi is another function. Okay, so it is a Ket, it is a Ket, there is no confusion that it is an operator. No, this is a function. So a psi within a Ket phi alpha a psi. So you can take a at the outside and alpha in the outside of the Ket, and if the a psi is in the bra, then a operator will be in the right hand side but in dagger form, that is Hermitian adjoint form will be written in the right hand side, and a will be come out of the bra, as you know, as a complex conjugate form, that is alpha star. So these are two very important relations you should keep in your mind, and this is this can be understood using your previous formula which I have talked already. Now an operator is to be called Hermitian when the Hermitian adjoint and the original operator are equal to each other, that is they are equal, that is a operator is equal to a dagger. So a operator or in other terms you can write psi a phi in bracket is equal to phi a psi whole star. If this is satisfied, then you can say that a is equal to a dagger. So it can be proved like this, that start from here in the left hand side, psi a phi. So a over phi is nothing but another Ket. It is written here. See, a operating on, say alpha is equal to 1. So a operator operating on Ket will give you another Ket. Within the Ket you can write a operator. So a psi Ket is equal to a operator operating on the Ket psi. The meaning is same. So it is written over here, a phi is equal to actually a phi ket. Now consider this a phi as new function x. So psi x in the bracket notation it is there, and it is equal to x psi whole star. It is using the bracket notation. It is proved here. Yes, there it is proved. Phi psi whole star is equal to psi phi. So phi x is equal to x phi x psi whole star. Now put the value of x, that is operator a into phi, a into phi, not into, a operating on phi, and in the ket there is psi and whole star is there. Now whole star, you can add, you can write this bra a phi and take the a at the right hand side as dagger. It is written over here. If you want to take the operator from the bra notation, then it will come at the right hand side and in Hermitian adjoint form. So a dagger psi, say alpha is equal to 1, so bra a psi is equal to bra psi, which is on which Hermitian adjoint is operating on. Okay, so see here, bra a phi is there, so phi bra, and in the right hand, from the right hand side a dagger is operating on phi. They are same meaning using the relation 6, and psi is there in the ket and whole star is also there. And now a dagger is equal to a according to the definition of Hermitian, then phi a psi whole star is equal to psi a phi. It is proved. If you assume this, you can prove this one. If you assume this, you can prove right this formula. I would like to prefer you assume that a is equal to a dagger and prove this relationship, then it will be easier, and this will consolidate that the operator a is Hermitian 1. Okay, and there are problems regarding the not matrix representation on the bracket notation. You can do it your own, just straightforward problems are there, and by doing these basic problems by your own, you can understand what is meant by bracket notation, what are the features of bracket notation, and how you will be serious in dealing with bracket notation. So it will be there, you just follow them and show that eigenvalues of Hermitian operators are real. It is just like the matrix. In case of matrix, you prove this, all this. In case of quantum mechanics, the proof is same, but using the bracket notations, using the bracket formula. Very simple formulas are there. You should try it by your own. And in my next class, I will come into the matrix representation of kets, bras and operators. So let me stop here. Thanks for your kind attention.